Alright, please read the problem.
So, a car of mass m, moving at a constant speed, of v turns around a bank curve of radius r. Draw a free body diagram and a total force diagram for the car as it moves on the curve.
What? We're like, take it before I better take it before
Alright, so I'm trying to draw like a car.
What? Why?
I'm copying that diagram essentially. But
No, you won't.
what I've done for that diagram is we've taken a slice out of the track. It's like if you look on, like you ever see races where the whole track is banked. So the whole track is tilted some angle theta. And what you'll notice is normal force is tilted, and it actually helps the race cars go around the turn at like a higher speed. So this would be our force diagram, weight and normal, and then I should do some reference lines, right?
No, I don't remember that.
There's some reference lines.
Did you have Miss Yang?
All right, and then
She went to
I need another reference line this way. So you would want to draw all those reference lines. And then you can see that this is the angle I know, right?
Yeah.
Which means that this is the same angle.
Yeah.
And normal force, when you tilt a surface, your normal force typically will tilt by the same exact amount that your surface is tilted from horizontal. So normal force gets tilted from the vertical the same amount that the surface gets tilted from horizontal. Alright.
What is lift exactly?
What is lift?
Yeah.
Oh, it's a different kind of subject.
Huh?
You're talking about lift. Okay, let me pause this. Alright, so where were we? This was our force diagram, and we identified our angles. And now, if I do my vector sum diagram, which way is the acceleration? This is normal. Tell me when to stop my weight. Which way does my acceleration need to be?
Acceleration. Go to the right.
Yeah, that's right. So my weight is down. Do you know why?
Pushing down.
Why? Well, why is my acceleration this way?
Because going to the right.
How do you know that your acceleration is to the right here?
Looking at the car.
Well, think of the path that the car is traveling in. We're assuming, again, that the car is traveling in uniform circular motion. So the car is moving in a circle, and this is a horizontal circle. Uniform means steady speed. Circle refers to the path of the object. So the car is moving in a circle with a constant speed. That's what we're assuming. And that circle is a horizontal circle, and that acceleration, this direction here, is pointing towards center of the circle. And that's what this direction is. It's towards center. Cool? And what's the length of that net force vector in this case? That's just the acceleration. What you gave me is the centripetal acceleration, v squared over r. But that's our net force. And our net force is equal to ma. And our net force is in the centripetal direction, or towards center. So our A is towards center. So you can plug in v squared over r for A. So again, what's the length of that vector?
V squared over r.
Sweet, dude. Alright. And we gotta find where our angle is, like in our diagram. So I'm thinking I look here, and that would be here, right? It's gotta be right, because that's the tail of my normal force. And this is between normal force and weight. So I think the problem's pretty much done. What are we looking for? What do we know? What's given?
So then derive an expression for the think angle theta at which friction would be necessary in terms of G, R, and V.
Okay, so given is G, R, and V, and we're supposed to find what? Angle theta?
Yeah.
So we want a theta where we don't even need friction to stay on the track. We want to find that angle. And clearly that angle is going to be bigger if we're going faster, or if we're in a different gravity field, or if the curve has a different radius. So these are the three things that are going to affect it. I think tangent is what we want here, because the angle that we know the opposite side and we know the adjacent side. We don't know that much about normal here, and we want everything in terms of G, R, and V. I'm thinking that's gonna probably work out. You can always just try it, see how it works, and if tangent doesn't work, we'll try it again. Tangent theta is what? MV squared. That's okay. Over R, and that's over what? MG. Did I do that right? I think that's opposite over adjacent. Yeah. And then what happens to our M's? So for part C, we're going to say the mass has no effect on banked angle.
Wait, does that affect because you don't?
It cancels out. It doesn't matter. We see it there. And then I'll finish off the equation. So tangent theta, it looks like if I multiply the top and bottom by 1 over G, right, then this G is gone. So I get V squared over RG. Is that right?
Yeah.
I think that's good. And then
Well, Sammy Hogg,
theta
please report to the counseling office.
is
Sammy Hogg,
the
please
angle
report to the counseling office. Your
whose
father's waiting for you.
tangent is V squared over RG. Right? That would be theta. Theta would be the angle whose tangent is that. So we're done. We found... Huh?
Why did you do the reciprocal?
Why did I multiply by the reciprocal? Well, that's how I got G out of the denominator. And if I multiply the numerator and the denominator by the same thing, essentially I'm multiplying by 1. Because anything divided by itself is 1. How did I know to do that? Just based on experience, I guess. I'm trying to get my G in the numerator and get it out of the denominator. Is what I'm trying to do there. Does that help?
Yeah.
Okay, I'll post this. Hopefully it helps.